In Part 4 we saw a bunkum explanation where geostationary satellites are claimed to be moving against the flow of space rotating around Earth in order to appear motionless. An ill-conceived analogy to explain this is that of a boat motoring against the flow of a river so that it stays in the same position relative. The first job for any space program, of course, is to get into space, otherwise you haven't got a space program. How does this work in a geocentric universe? Everything in the sky supposedly rotates from east to west. With viscous space, it makes sense that the geocentrist rocket should not be launched against the flow, but rather with it. The geocentrist can use less fuel getting into space that way, and they can do this by either heading straight up, or preferably by heading west. With a static Earth and frictionless space, a geocentrist can launch rockets from anywhere and in any direction, with no difference in fuel consumption. With viscous space, rocket science for the geocentrist is easy. They can simply point a spacecraft at its destination and let it travel a straight line through rotating space. Of course, there is a slight problem with this idea. A geocentrist sending a probe to Mars must, like his heliocentrist counterpart, take account of where the planet will be in future. Here the similarity ends. Geocentrists have no mathematics to describe or predict the motion of anything, so they're a bit stuffed. Perhaps frictionless space can help. With return. The Mars Reconnaissance Orbiter was sent to the red planet with a fuel tank containing 1,187 kilograms of hydrazine. Over 70% of that fuel was used in one maneuver, a 27-minute-long rocket burn for orbital insertion. This put it into an elliptical orbit with a periapsis 400 kilometers above the surface and an apoapsis of 44,500 kilometers. MRO then spent 6 months using Mars' atmosphere to gradually shape its orbit into its near-circular one, ranging from 255 to 320 kilometers above the Martian surface. This long aerobraking phase meant the amount of fuel needed on the craft was almost halved. How fast does MRO travel around its orbit? We can get a fair estimate for this since its orbit is nearly circular, and the mass of MRO is insignificant compared to that of Mars. We'll use this formula. The average speed is the root of gm over a. G is the now familiar universal gravitational constant, m is the mass of Mars, and a is the semi-major axis of the orbit, for which we'll use the equatorial radius of Mars plus the altitude of MRO's orbit at around 300 kilometers. Crunch the numbers, and MRO's orbital speed is 3.4 kilometers per second. If Mars is flying through space, simple universal physics explains much that geocentrism can't, in that it explains everything that geocentrism can't. But how else do we know that Earth isn't the mysteriously inexplicable center of the universe? Changes in Earth's position and velocity result in observable effects that are either explicable by a moving Earth or by more layers of hand-waving physics-defying horse shit. In this part we'll find out which is most likely. Let's start with position. Everyone knows that if you move in any direction, nearby objects move within your field of view far more than distant ones. This apparent displacement of objects between different lines of sight is parallax, and it's the basis of our depth perception. Measuring the distance to an object using parallax is simply a case of trigonometry. If you want to know how far away some landmark is, you can move some distance b perpendicular to the original line of sight, and measure the change in angle needed to point at the landmark again. You can then work out the distance using the bog standard tangent formula. What's true for landmarks is true for anything else, at any distance. The more distant the object is, though, the smaller the angle of parallax. This initially posed problems, as even the nearest stars are so far away that the angles involved are very small. In the late 1500s, Tycho Brahe attempted to measure parallax. He started with the supernova of 1572, but being over 8,000 light-years away, it was beyond his ability to measure it. He didn't know that at the time, of course. He tried measuring parallax of stars too, and failed. This isn't surprising when one considers that Brahe was working without a telescope. He died in 1601, before its invention in 1608. Brahe's measurements were as good as possible with the naked eye. His stellar and planetary positions were accurate to a mean error of 2 arc minutes. They were accurate enough for his assistant, Johannes Kepler, to determine that planets orbit the Sun in elliptical orbits, and to formulate his 3 laws of orbital motion, which we saw in Part 2. Limited to this degree of accuracy, though, Brahe simply stood no chance of measuring parallax.